just a few millimeters thick, yet capable of opening the borders of nearly the entire planet. A passport is no longer just a document. It has become a mobility key, shaping the fate of more than 8 billion people worldwide. But have you ever wondered how this powerful booklet is actually made? The journey of a passport does not begin in a printing room, but in vast cotton and flax fields, where ordinary fibers are carefully selected to create a type of security paper that can endure thousands of stamps. From there, they move into highly controlled facilities, similar to banknote printing plants, before becoming a travel pass that determines which parts of the world you are allowed to enter. Today, join Agriculture Insight as we explore the process behind passport production, uncovering the security secrets hidden within this small yet tightly controlled booklet, an integral part of national security systems. Every year, more than 150 million passports are produced, each embedded with up to 30 of the most advanced security layers available. But their true value does not lie in technology, it lies in the power of the nation behind them. A passport from Singapore or South Korea can unlock access to more than 190 destinations, while Afghanistan remains below 30. The shape is the same, the size is the same, yet the freedom of movement differs by an entire world. In reality, passports are not a modern invention, as many people assume. More than 2,500 years ago, Persian kings issued the first letters of passage, but it was only after World War I that passports were standardized into a global border control system. During World War II, Chiune Sugihara wrote more than 2,000 visas by hand, helping around 6,000 Jewish people escape Europe. At that moment, a passport was not just a document, but the line between life and despair. Many people still confuse passports with visas, yet they are two completely different gates. A passport proves who you are to the world, while a visa determines whether you are allowed to enter a country. That is why millions of entry applications are rejected every year. And according to Interpol, more than 232,000 cases of stolen or forged travel documents were detected at international borders in 2023 alone. What about you? Have you ever run into trouble with immigration procedures? The process of creating a passport does not begin at the printing press, but at the design table, where every detail is calculated to reflect national identity while integrating sophisticated layers of security. A modern passport typically consists of three main components: security paper, a polycarbonate data page, and an RFID chip for storing information. From this foundation, design is no longer just an aesthetic element, but becomes the first layer of physical authentication. Each passport is essentially a unique, light signature of its nation, a recognition system that is nearly impossible to replicate. The Belgian passport hides an entire universe of Tintin, the globally famous adventurous reporter from the classic comic series by Hergé, visible only under UV light. Canada's passport illuminates the aurora borealis and the iconic red maple leaf across its pages, while the United States passport stands out with the bald eagle and founding symbols. These seemingly artistic details are, in fact, highly sophisticated optical security features, where national identity is encoded directly into light. But design is only half the story. The rest of the passport begins with its raw materials. Passport paper is not ordinary paper. It is made from security-grade cotton fibers, sometimes blended with linen, the same type of material used in banknote printing. With cotton, the fiber supply mainly comes from the southern United States, where the climate produces long, white, and durable fibers that meet the strict standards required for high-security manufacturing. From these qualified cotton fields, the selection process becomes far more rigorous than in textile production. During harvest season, high-capacity machines can collect over 2,000 kilograms of cotton per hour, but only about 10 to 12% meets the criteria for security paper production. Rotating spindles, fitted with hundreds of small picking heads, continuously pull fibers from the bolls, minimizing impurities directly in the field, before the cotton is quickly compressed into large bales weighing around 200 to 220 kilograms for transport. These harvested cotton bales are transported to staging areas at the factory before officially entering the processing line. Here, a fully automated system begins opening the fibers, breaking apart the tightly compressed masses, while simultaneously removing dry leaves, small twigs, and fine dust through a combination of rotation, vibration, and high-speed compressed air. This process not only cleans the cotton, but also loosens and evens out the fibers, preparing them for the next stages. After that, ginning machines continue separating the seeds from the cotton, retaining only the purest fibers, the core raw material for the entire textile industry that follows. If the US dollar is known for its 75 to 25 ratio of cotton to linen, passport paper also uses these two fibers, but the exact ratio is kept confidential. Alongside cotton, linen fibers are added to enhance strength, stability, and resistance to twisting in each page. In farming regions of the northern United States, flax is harvested using specialized pulling machines that extract the entire plant from the ground rather than cutting it, preserving the full fiber length, an essential factor that determines the toughness and durability of each passport page. The nearly 1 meter long flax stalks are then laid out in parallel rows across the fields and left to dry naturally for several weeks to reach a stable fiber state. Once they achieve the required level of maturity, they are gathered by machines and rolled into large bales weighing around 300 kilograms, ready for the next stage in the security paper production process. After that, the flax is crushed, combed, and refined before being blended with cotton pulp. This combination creates a type of paper that is soft enough for printing, yet strong enough to carry a person's identity through hundreds of inspections without structural degradation. As soon as the raw cotton and flax bales arrive at the factory, the journey to create one of the world's most powerful base papers begins, where everything familiar immediately becomes something entirely different. The fibers are cleaned and then mixed into large vats, forming a slurry similar to thin porridge, where thousands of microscopic security fibers, just a few millimeters long, along with invisible identifiers, are deeply embedded into the material structure. From there, the mixture is continuously spread onto a sheet-forming system, pressed down to a thickness of only about 90 to 120 micrometers, and then dried under strictly controlled conditions before being rolled into large sheets. Everything is then wound into reels and transferred to secure printing facilities. This type of paper never appears on the civilian market and is regulated as strictly as national currency. In many countries, the unauthorized production or possession of this material can lead to criminal prosecution. Once the base layer is complete, the printing stage truly begins, where every detail is transformed into a national fingerprint. Aluminum plates coated with ultra-sensitive carbon layers are engraved with micrometer-level precision, storing the entire design in a form that the naked eye cannot fully perceive. The excess carbon is then removed using specialized rollers and brushes. The plates are cleaned, dried, and fed into a synchronized multi-station printing line. Here, layers of security inks, blue, red, green, and black, are overlaid using offset and intaglio printing technologies, with each layer carrying a specific visual element and anti-counterfeiting function. As the multi-layer security paper passes through, rubber rollers transfer the colors onto the surface with a tolerance of less than 0.01 millimeters, forcing every detail to align perfectly. Even the slightest misalignment would render the pattern incomplete and impossible to replicate without every single layer. Under ultraviolet light, 6mm security fibers begin to glow, confirming that this is no longer ordinary printed paper, but a passport page in the making, where identity is encoded directly into the material itself. But a passport does not stop at paper, because its core lies in the polycarbonate data page, where the chip is integrated from the very beginning, an electronic brain that does not yet carry an identity. This chip is essentially a tiny RFID microchip, capable of storing and transmitting data contactlessly when passing through control gates. Inside, it is designed to hold biometric images, personal information, and encrypted security keys. But at this stage, it has not yet been activated or encoded. The entire system only truly awakens during the personalization process, transforming it into an inseparable part of a person's digital identity. Once the data page has the chip embedded, all components move into the booklet assembly line. Specialized stitching and pressing systems secure each page with extremely high precision, while the spine is creased using a specially designed blunt blade to shape the structure without damaging the internal security layers. At this stage, the passport is physically complete, but it still does not belong to anyone. Immediately after that comes the most critical step, the one that transforms an anonymous passport into a legally valid identity: personalization. Before this stage, each citizen's biometric data has already been collected and verified within the system. Only then does personalization officially begin. The portrait, ID number, and all personal information are laser engraved directly into the multi-layer polycarbonate structure. When the laser interacts with the material, it alters its color at a microscopic level, producing extremely high-resolution images that are nearly impossible to modify or counterfeit, the moment an anonymous passport officially becomes a citizen's legal identity. After personalization is complete, each passport must undergo strict security checks, including RFID chip readability, data accuracy, and the response of security inks under UV light. It is then registered and activated within the National Identification System, the point at which it officially becomes valid for international use. From that moment on, a passport is no longer just a paper booklet. It becomes a nationally issued identity document that must be protected throughout its entire lifespan. That is why passport covers exist as a simple yet effective armor, from moisture-treated genuine leather to modern materials like polyurethane and waterproof PVC, even incorporating RFID blocking layers to prevent unauthorized data scanning. Thanks to this small layer of protection, a passport can accompany you through hundreds of security checks, carrying your identity across borders worldwide. Aluminum is one of the most abundant metals in the Earth's crust, accounting for about 8% by mass, but it does not exist in a pure form. Instead, it is always locked within ores. Before the Hall-Héroult process was introduced in 1886, extracting aluminum at an industrial scale was nearly impossible. As a result, production costs were so high that the metal was once considered a luxury, even more expensive than gold. A striking example, Napoleon III used aluminum utensils to entertain VIP guests, while others were served with gold. Aluminum is also often confused with steel or silver because they all share a bright metallic appearance. However, unlike steel, which is heavy and magnetic, aluminum is significantly lighter and is completely non-magnetic. As for silver, although it looks quite similar, what we commonly call foil in everyday life is actually made almost entirely of aluminum, simply because real silver is far too expensive to be used in that way. Today, the world produces around 70 to 75 million tons of aluminum each year, while recycling tens of millions of tons from various sources. Notably, China, which accounts for more than half of global output, is accelerating recycling efforts as part of its strategy to reduce energy pressure and control emissions, with a scale more than 3 times that of the United States. In an era of rising energy costs, recycled aluminum is no longer just an environmental solution. It is becoming a force that is reshaping the entire global metal supply chain. The journey of aluminum's rebirth begins in places that are often overlooked: trash bins, scrap yards, and collection points across cities. Used beverage cans, discarded metal fragments from daily life and industrial production are gathered from multiple sources, ranging from households to industrial facilities. Thanks to its high recovery value, aluminum is rarely left behind. Instead, it is almost always reclaimed through recycling systems, scrap collection networks, or specialized recovery programs. After collection, the aluminum does not immediately enter processing plants. Instead, it is transported to intermediate consolidation facilities. Here, it is accumulated and compressed into large bales for easier storage and industrial-scale transportation. This marks a crucial transition, moving from scattered individual items spread across different locations. Aluminum is gradually consolidated into a large, unified stream of raw material, ready for the next stages of intensive processing inside recycling facilities. After being collected and transported to the recycling facility, aluminum enters the sorting stage, a critical process that determines the quality of the entire recycling chain. At this point, large bales of scrap aluminum are placed onto conveyor belts and pass through a series of automated separation systems. Magnets are used to remove ferrous metals, while eddy current technology helps separate aluminum from plastics, glass, and other non-conductive materials. Beyond that, aluminum is further sorted in detail according to alloy types and intended applications, such as beverage cans, industrial aluminum, or construction materials. Even slight differences in metal composition can affect the quality of the final product, making precision at this stage extremely important. Once sorting is complete, the aluminum is effectively material cleaned and ready for the next stages of processing. After sorting, the aluminum is fed into high-capacity crushing systems, where cans and metal fragments are cut and broken down into thousands of smaller pieces. Under the force of intense cutting and impact, the original rigid structure is completely broken apart, turning the aluminum into uniform shreds that are easier to process. This step does more than simply reduce size. It plays a crucial role in optimizing the subsequent stages. Once the aluminum is shredded, its surface area increases significantly, allowing processing to occur faster, more efficiently, and with lower energy consumption. At the same time, the improved uniformity and particle size helps ensure better control over metal quality throughout the recycling process. After being shredded, the aluminum moves on to a deep cleaning stage to remove any remaining impurities. Although it has already been sorted, the metal surface may still carry layers of paint, ink, grease, and organic compounds left from its previous use. The aluminum pieces are passed through thermal and mechanical treatment systems, where high temperatures help break down and burn off paint, printing ink, and organic residues. At the same time, additional separation and filtration systems remove any remaining ash and fine particles, leaving the metal surface cleaner and more uniform. This is a particularly critical step, as even a small amount of residual contamination can directly affect the quality of aluminum after melting. After impurities have been removed, the aluminum is transferred into industrial furnaces, where temperatures are raised to around 660 degrees Celsius, high enough to completely melt the metal. Under extreme heat, solid aluminum pieces begin to soften, deform, and gradually lose their original structure, merging into a glowing stream of liquid metal. During this process, aluminum is not simply melted, it also undergoes a form of refining. Lighter impurities such as residual paint, dust, and unwanted compounds rise to the surface as slag and are removed. At the same time, the high temperature fully breaks down old bonds, allowing the aluminum to return to a more uniform and purified state. Modern furnaces are designed to precisely control temperature and internal conditions, ensuring even melting, minimizing material loss, and preserving optimal quality. Once formed, the molten aluminum is kept in a stable state, ready for the next stages of production in the processing line. After reaching a molten and purified state, the liquid aluminum is transferred directly from the furnace into casting systems. Here, the glowing stream of metal is poured into large molds, where it begins the transition from liquid to solid. Depending on its intended use, aluminum can be cast into large ingots, thick slabs, or long billets, serving as intermediate raw materials for subsequent processing stages. This casting process requires strict control of both temperature and cooling rate. If cooling occurs too quickly or unevenly, the metal's internal structure may be compromised, leading to reduced quality. Conversely, when properly controlled, aluminum solidifies into a stable structure with the required strength and durability. As the molten metal gradually cools and hardens within the mold, aluminum once again takes shape, but this time, not as scattered fragments as before, but as uniform solid blocks of metal, ready for the next stage of processing. After the aluminum has been poured into molds and begins to solidify, the metal blocks cannot be removed immediately. At this stage, they are cooled with water, typically through continuous external water spraying systems that rapidly reduce the temperature and stabilize the internal metal structure. The strong flow of water strikes the red-hot surface, producing thick clouds of steam, a clear sign that the cooling process is actively underway. Once the temperature drops to a safe level and the aluminum has fully solidified, industrial cranes come into operation. Massive cylindrical aluminum blocks, weighing several tons, are securely gripped by specialized mechanical clamps and carefully lifted out of the molds with high precision before being placed onto the factory floor. This entire process requires close coordination between machinery and technicians to ensure the blocks are not deformed or damaged during handling. At this point, the surface of the ingot still retains characteristic wave-like textures formed during solidification, while internal heat has not yet fully dissipated, meaning they must continue to be carefully monitored and controlled before moving on to the next stage. After cooling, aluminum slabs are fed into the rolling line, one of the most critical stages that directly determines the quality of the final cans. Here, the aluminum passes through a series of high-strength steel rollers where it is subjected to extreme pressure to gradually reduce its thickness. From blocks tens of centimeters thick, the aluminum is rolled through multiple stages, with each pass only slightly reducing thickness to avoid damaging the metal's internal structure. This process typically combines both hot rolling and cold rolling. In the initial stage, aluminum is rolled while still at high temperature, making it easier to deform and requiring less force. It then continues through cold rolling at lower temperatures, which increases strength, hardness, and improves surface finish. Between rolling cycles, annealing treatments are applied to restore the metal's ductility after it has hardened due to deformation. The result of the entire process is extremely thin aluminum sheets, typically around 0.2 to 0.3 millimeters thick for beverage cans, while still maintaining high strength, pressure resistance, and uniformity. These sheets are then wound into large coils, weighing up to tens of tons, and transported directly to production lines, where they will be stamped and shaped into finished cans. From these thin aluminum coils, the material enters high-speed stamping lines, where it is cut into circular discs and then deep drawn into the initial cup shape. From there, these aluminum cups are further stretched and thinned into can bodies through a drawing and ironing process, reducing wall thickness while maintaining the necessary strength. The rim of the can is precisely trimmed and formed to fit the lid, while the body is cleaned, printed, and coated with an internal protective layer to ensure food safety. Finally, the completed cans undergo a series of rigorous quality control checks, including tests for airtightness, structural integrity, and dimensional accuracy. They are then stacked and packaged in large batches, ready to be transported to filling plants. There, the cans are cleaned one final time, filled with beverages, sealed and labeled before being released to the market, appearing on store shelves as fully finished products, ready to reach consumers. Unlike most other materials, aluminum never truly reaches the end of its life cycle. It simply keeps transforming from one form to another, again and again. With each recycling cycle, aluminum not only retains its original quality, but also saves a tremendous amount of energy compared to producing it from raw materials. This is what makes aluminum one of the most sustainable materials ever created, where the concept of waste almost doesn't exist, but instead marks the beginning of yet another life cycle. Every year, more than 300 million tons of salt are extracted worldwide, an amount so vast that if gathered together, it could blanket all of New York City beneath a layer of salt tens of meters thick. From these tiny crystals emerges the foundation of countless essential industries, the maintenance of biological balance, and the direct sustenance of all humankind. Yet within this immense volume, only a rare few rise beyond the role of a simple seasoning to become cultural heritage. Asin tibuak, crystallized from coconut husk ash and fired clay, with a deep mineral character and a whisper of smoke. Kalanamak, sharp-edged with its unmistakable sulfurous aroma. Bamboo salt, rounded and savory, leaving a warm mineral finish after 9 firings over open flame. And Guérande, pure and delicate, lightly crisp and slow to dissolve in the sea breeze of France. Today, join Agriculture Insight as we delve into the journey of the 4 most expensive and rare salts on the planet, where essence is distilled from humble raw materials, artisanal craftsmanship creates luxury, and hidden minerals become culinary symbols of an entire region's identity. Our first stop brings us to Bohol Island, a land of heritage coconut groves and some of the saltiest tidal waters in the Philippines. Here, Asin tibuak, one of the rarest salts on Earth, stands on the brink of extinction, with fewer than 5 families still preserving its traditional, closely guarded craft. The process begins with the careful selection of fully matured coconuts. The first step is husking, during which skilled artisans remove the shell and flesh, preserving only the thick, fibrous husk, the sole material whose capillary structure is perfectly suited to absorbing and retaining salt crystals. These husks are then densely packed into coastal marsh pits known as bonbon, where they are submerged in seawater for 3 to 6 months. Guided by the rhythm of the tides, the coconut fibers act as both a natural filter and reservoir, quietly drawing salt and oceanic minerals deep into every strand. At this stage, a natural exchange reaction takes place. The interaction between tannins in the coconut husk and trace minerals from the seawater gradually turns the fibers a distinctive black, clear evidence that the husks are fully mineralized. This transformation signals the artisans that the husks are ready to be retrieved and dried under the intense tropical sun. Once the mineral concentration reaches its ideal level, thousands of coconut husks are loaded onto bamboo rafts and transported to the processing site. At the workshop, the salt-soaked coconut husks are stacked into large mounds and burned continuously for 7 full days. Throughout this intense transformation by fire, artisans maintain a constant 24/7 watch, carefully controlling the temperature while repeatedly dousing the burning husks with seawater. Under the force of extreme heat, moisture evaporates, leaving salt and oceanic minerals to concentrate and accumulate, transforming the ash into a dense mineral reservoir. The final product is gasang, a fine white ash with an exceptionally high salt content. With the saline ash prepared, the process shifts to the construction of a natural filtration system. Fresh bori palm leaves are cut into sections approximately 40 centimeters long, then layered and interwoven to line the interior of massive bamboo funnels. The choice of bori leaves is a deliberate technical decision. Their rigid veins withstand the pressure of the ash mass, while their naturally water-resistant surface channels the concentrated salt solution downward without loss. Once securely reinforced, the gasang ash is poured in and compacted into a uniform block, after which artisans begin the leaching process using thousands of liters of seawater. Over the course of several hours, the water percolates through the ash, dissolving the concentrated salt crystals and trace oceanic minerals. At this stage, the ash functions like a natural carbon filter, removing impurities and leaving behind only the purest essence. Tasik, an amber-colored liquid with a saturated mineral concentration, nearly 10 times saltier than seawater. Yet it is precisely this saturated salinity that creates the ideal conditions for crystallization. At the firing site, hundreds of hand-molded clay pots are packed tightly together atop long hearths built from hardened ash and stone. This seamless arrangement forms a uniform heat-retaining surface maintained at 200 to 300 degrees Celsius, minimizing energy loss and ensuring that every vessel is subjected to the same intensity of flame. The oval shape of each pot is equally intentional. Its structure optimizes convective heat flow, forcing salt crystals to form evenly from the core outward. Notably, each pot is used only once, rendering every salt block a singular, unrepeatable creation. To prevent thermal shock and structural cracking, artisans keep a pan of tussock boiling constantly nearby, replenishing the pots with hot liquid continuously over 24 hours. This sustained pressure of concentration is the decisive factor, allowing salt crystals to compact tightly, bond durably, and achieve absolute density uniformity from the base to the rim of the vessel. After roughly a full day and night, when thermal cracks begin to run along the body of the clay pots, a clear sign that the salt blocks have fully matured and all residual moisture has escaped, the kiln is finally allowed to go dark. Cooling then occurs naturally, enabling the salt to stabilize its structure and compact further from within. The result is Asin Tibuok in its finished form. Stone-hard, uniquely oval blocks with a sharp, assertive salinity, a gentle smoky finish, and faint fruity notes drawn from the coconut husk. Priced at up to USD 100 per block, on par with England's famed Malden Salt Company, or premium smoked salts from the Pacific Northwest, Asin Tibuok is often shaved directly over dishes by discerning chefs, used as a luxurious finishing salt. In its homeland of the Philippines, however, this salt is the soul of humble fare. From bowls of lugaw rice porridge to crisp green mangoes, where its smoky depth elevates the simplest ingredients into something unforgettable. Leaving Southeast Asia behind, the journey continues with kala namak, a salt that also forms into rounded but rugged blocks, marked by a deep reddish-black hue and a distinctive sulfur aroma reminiscent of boiled eggs. Its salinity is dry, sharp, and intensely mineral, leaving a bold, lingering finish rarely found in other salts. Originating in northern India at the foothills of the Himalaya, Kala Namak is produced from pristine rock salt deposits dating back 800 million years, transformed through a deliberate process of firing and chemical conversion. The process begins with the preparation of cylindrical kilns, solidly constructed from refractory bricks and clay. The fuel used is a distinctive blend of charcoal, tree bark, and dried cow dung. This combination is chosen not merely for its heat output, but to establish a reducing environment within the kiln. Such conditions are essential for chemical reactions to proceed in isolation from external oxidation, laying a stable foundation for the transformation of the salt's physical and chemical properties. Himalayan rock salt is first crushed into smaller pieces before being loaded into earthenware pots and tightly sealed with clay lids. The kiln is then fired continuously for approximately 24 hours, allowing temperatures to rise beyond 800 degrees Celsius. At this extreme threshold, the salt does more than heat up. It fully melts into a liquid state. This molten phase is the key mechanism of the process, enabling trace minerals to reorganize their structure and creating the conditions for thorough chemical interactions with organic additives introduced at later stages. Once the salt has fully melted, artisans add harad seeds along with an additional amount of charcoal. This is the most critical stage of the entire process, as it ultimately determines the quality of the finished salt. Organic compounds within the harad seeds act as powerful reducing agents, stripping oxygen from sulfate groups naturally present in the rock salt and converting them into sulfides. It is this reaction that releases sulfur compounds, producing the distinctive aroma reminiscent of cooked eggs and imparting the salt with its deep purplish-black hue through the formation of iron sulfide. Once the firing cycle is complete, the kiln is not rapidly cooled. Instead, it is left to cool naturally over 2 to 3 days. This slow cooling process allows the salt crystals to recrystallize into a tightly compacted mass, achieving a hardness comparable to that of gemstones. When the clay pots are finally broken open, the salt emerges with its signature deep purplish-black color. Yet a fascinating paradox occurs. The darker the solid salt block, the lighter, pale pinkish gray, the color becomes once it is finely ground. This phenomenon results from light scattering across ultrafine sulfur particles, a key chemical component responsible for the salt's distinctive character. After this meticulous journey, Kala Namak is sifted, ground, and packaged for market. From a medicinal perspective, it is regarded as a cooling salt, prized for its digestive benefits, its ability to reduce bloating, and its superior effectiveness in maintaining electrolyte balance compared to conventional white salt. Since ancient times, humans have used bamboo as a vessel for storing food, but only in Korea has this plant been elevated into a biological furnace, giving rise to one of the most expensive salts on Earth, 9 times fired purple bamboo salt. The journey begins with the careful selection of moso bamboo, aged 3 to 5 years, the stage at which bamboo sap contains its highest concentration of silicon and trace minerals. In heritage bamboo forests, only culms that meet strict standards of thickness and maturity are harvested, then cut into uniform sections, leaving one natural node intact to create exceptionally durable containers. Inside the workshops, artisans hand-pack pure sea salt into each bamboo tube. To achieve the required density, the salt is compressed under intense pressure to eliminate all air pockets, a critical technique that ensures full contact between the salt crystals and the bamboo walls, while preventing internal air expansion that could cause the tubes to rupture during firing. The decisive step in this stage is sealing the open end with mineral-rich yellow clay. Technically, this clay acts as a pressure lock. It prevents the salt from escaping while forcing the bamboo's valuable sap to be driven back into the salt core under the force of the kiln, allowing the bamboo's minerals to fully permeate the salt. To initiate the transformation, the tightly sealed bamboo tubes are stood upright inside stone kilns, fired exclusively with pine wood to produce stable heat and a clean, aromatic flame. During the first firing at 800 degrees Celsius, the bamboo casing burns away completely, releasing abundant sap that flows outward to envelop the salt core. This layer of bamboo resin, together with pine essential oils, acts as a natural catalyst, neutralizing acidic compounds and removing heavy metals from the raw sea salt. Yet a single firing is not enough to achieve absolute purity. After each cycle, the solidified salt is removed, crushed into a fine powder, and repacked into fresh bamboo tubes to begin the next round. This process continues for more than 30 days, culminating in the 9th firing, when temperatures are driven to extreme levels exceeding 1,300 degrees Celsius. At this point, the salt undergoes a complete physical transformation. Its crystals no longer remain solid, but melt and flow like molten lava, glowing red-hot within the kiln. Though labor-intensive and exacting, this prolonged ritual is a definitive commitment to quality. With each passage through fire, concentrations of potassium, magnesium, and organic sulfur are further intensified, while residual impurities are fully broken down, gradually shifting the salt's color from ashen gray to a deep, mystical purple, and endowing it with exceptional antioxidant properties. To recover the finished product, artisans must use specialized steel rods to guide the thick, molten salt out of the kiln before it has a chance to solidify. As it cools, this molten mass recrystallizes into amber-hard slabs of salt, marked by their signature deep purple hue. What follows is a rigorous process of selection. Each slab is broken apart by hand to remove all traces of ash and residue, preserving only the purest inner core. The final salt delivers a profound salinity, followed by an unmistakable finish of pinewood smoke. On average, producing just 1 kilogram of purple bamboo salt requires the consumption of tens of kilograms of raw salt and several tons of pine wood, burned continuously over many days. This extreme expenditure of materials combined with intense thermal pressure fundamentally alters the salt's mineral structure, elevating it far beyond the role of a simple seasoning. Instead, bamboo salt becomes a therapeutic mineral substance, prized for its alkalinity and powerful detoxifying properties. This is why it holds a central place in deep cleansing and holistic wellness regimens, an achievement that ordinary sea salt can rarely attain. Eating a banana means throwing away the peel. That's obvious. But did you know that in many tropical countries, especially the Philippines and India, nothing from this zero-waste plant is discarded, not even the trunk? What was once cut down and left behind after each harvest is now collected, stripped into fiber, and recycled into high-value natural materials, generating tens of millions of US dollars each year for local communities. In the Philippines, the cradle of the global banana fiber industry, the Abaca banana is cultivated exclusively for fiber across hundreds of thousands of hectares, providing livelihoods for more than 1 million farmers and rural workers. Each year, this fiber brings in over 100 million USD for the Philippines and is recognized worldwide as one of the most durable, water-resistant, and strategically valuable natural fibers in the world. To produce natural banana fiber, the first step begins right in the field. After the banana bunches are harvested, the trunk is immediately cut down while the fiber content is at its optimal quality. A single decisive and precise cut is enough to bring down a banana trunk weighing dozens of kilograms. No machine can replace the hands and experience of farmers at this stage, as even a slight mistake in timing or cutting angle can significantly reduce the quality of the fiber obtained. After being cut down, the entire banana trunk is quickly loaded onto trucks and transported to a pre-processing facility near the field as fast as possible to prevent moisture loss and fiber oxidation. At this stage, the banana trunk is split lengthwise and peeled into individual sheaths. This is a critical step that directly determines the length and uniformity of the fiber, requiring steady hand control and practical experience. Ideally, the outer sheaths, where the cellulose fiber bundles are fully developed, yield the longest, strongest fibers with the least impurities. Farmers use specialized knives to carefully separate each layer along the natural fiber grain, avoiding damage or breakage to the fiber bundles inside. Despite modern tools, this step remains difficult to automate, as variations in trunk thickness and fiber structure still require human judgment. Each banana sheath is fed through a mechanical press or a manual stripping table to remove the soft pulp, leaving behind long bundles of cellulose fibers. Steady hand movements and precisely controlled pressure prevent the fibers from breaking, producing rough fiber strands with a characteristic ivory color. In practice, this work is far from easy, as the worker's sense of pressure combined with a consistent rhythm is a skill that often takes years for newcomers to master. After several hours of continuous processing, the result is bundles of raw fibers free of sap and retaining their full length, but still high in moisture and prone to discoloration if not washed and treated promptly. The raw fibers are then washed repeatedly with clean water, sometimes combined with mild biological enzymes to remove sap and impurities without damaging the fiber structure. Some facilities may use warm water to improve cleaning efficiency, or for fibers intended for paper production and coarse materials, apply stronger heat treatment to shorten processing time and reduce costs. Finally, the fibers are dried under natural sunlight or at low temperatures until they reach standard moisture levels, a process that typically takes at least 2 days. In major banana growing countries, such as the Philippines, India, and Indonesia, banana fibers are traditionally sun-dried on bamboo racks or raised wooden frames under natural sunlight, allowing the fibers to dry evenly while maintaining their light color and strength. Once dried, the banana fibers become lightweight, durable, and flexible, ready to move on to sorting, spinning, and industrial production stages. Tens of thousands of tons of banana fiber are collected and sent to industrial textile mills and fiber processing facilities, where it is determined whether they will become fabric, rope, or natural mats. Once inside the factory, raw banana fiber must undergo the most fundamental and critical step, carding. Here, fiber bundles are loosened, straightened, and aligned in parallel, while short fibers, broken strands, and remaining impurities are removed. This process standardizes fiber length, fineness, and uniformity, creating a solid technical foundation for the subsequent spinning and weaving stages. After carding, the fibers are fed into the spinning system, where they are twisted under tightly controlled tension and speed. In actual production, banana fiber is rarely used in its 100% form, but is commonly blended with cotton, linen, or other bio-based fibers to enhance softness, strength, and weavability, meeting the demands of industrial manufacturing. The result is stable yarn wound into spools, ready for weaving, carpet making, or the production of finished textile products. Depending on the intended use, the yarn is fed into shuttle looms, knitting machines, or braiding machines to produce fabrics, bags, mats, or technical materials. Compared to cotton, this material stands out for its higher tensile strength, but requires blending to improve softness. When compared with jute, banana fiber is lighter and more flexible, allowing it to be used in products with higher aesthetic requirements. In packaging and interior applications, its load-bearing capacity and stability in humid environments give it an advantage over many other plant-based fibers. In sustainable fashion, it is seen as an intermediate option, balancing performance and environmental impact. In terms of cost, a garment made from banana fiber or banana-blended yarn currently sells for about 20 to 40% more than a standard cotton garment due to higher collection and processing costs and the still limited scale of production. This remains the main barrier preventing banana fiber from becoming mainstream, as supply chains are still in the process of expansion and optimization. Each year, hundreds of millions of tons of banana trunks are reused instead of being burned, helping to reduce emissions by 20 to 30% in countries where bananas are a major crop. Easing environmental pressure and turning agricultural byproducts into part of the solution for a global green economy.